Thank you for coming, and thanks to the organizers for having me. Actually, second time, because I've been on the first PyCon in Czech in 2016 in Brno, I guess. This time, I would like to tell you a little bit about Git and how it works underneath. A few words about me. I'm, as said, Dariusz Aniszewski. I came here from Poland, from Warsaw. I'm a lead software engineer at Polidia. It's a design and development studio from Warsaw. I take care of a team of 14 wonderful engineers. And my history with version control actually started like 14 years ago, maybe at the university, when I mainly use Subversion. Once I started working in Polidia, we had Mercurial at the time. About 7 years ago, we switched to Git. And for a long, long time, I was just using Git. Like, I didn't know what's happening inside of it. I just used it. And it was actually okay. But at some point of time, I figured out that basically this tool holds everything I have done with my hands and my brain. Maybe it's a good idea to actually check what's happening inside. So I did. And it's actually pretty nice. And therefore, I would like to share it. And during the next about 20 minutes, I will basically show you some small theory, and there will be also a live demonstration of the Git internals. A lot of you probably, if you think about Git, think about what you can do with it. So you can add things to Git. You can commit things to the directory, to repository. So you can push your changes or pull changes from the remote, right? Basically, you're thinking about Git as a black box that has a set of APIs, can do certain things without really thinking what's going underneath. So you can kind of compare it to the bathroom sink that you use day by day to wash your hands. That has a limited set of features. You just use it. You don't know anything about the plumbing that is underneath. But without this plumbing, the sink will be useless. And this analogy is not made by me. This is like an official documentation of Git, and the plumbing and Porcelain concept is within their docs. The idea is that the Porcelain is something that is user-facing. It's designed for high-level operations, while plumbing is something that usually we don't need to see, to know about, but it works, and they are used by the Porcelain commands. And what I really want to tell you today is that Git essentially is a content addressable database. It uses SHA to identify the objects within the database. Basically, everything inside of Git is a file, a binary. It does hold snapshots, not diffs. I will tell you about it in a few seconds. In generally, it only adds things to the repo. And down the line, it's actually very easy. Let's take a look at the 3 types of objects that operates on the Git. We have blobs, we have trees, and we have files. The blob is simple binary large object. It's tempting to confuse it with a file, but the file has some attributes like its name or permissions. The blob is just the content of the file. And it can be hashed. And then we have this magical SHA. And to hash actually a blob is very easy, because I need to have the type of the content, which is the blob, then followed by space, followed by number of characters within the content, or actually the length of the content, followed by the null byte and the content itself. During the demo, I will show that this actually works. There is also a tree object. It contains information about the directory structure. As mentioned before, blobs is only for the content. You need a tree to know that this blob is in certain place in the directory structure. It holds information about the item name, so either file name or a directory name. It has a SHA for the object, either blob or another tree, and the file permissions. And last, we have a commit. That's like a top-level object. It does have references to the parent commits or commit. It has a reference to the tree, some author info, obviously a commit message, and possibly it can have other attributes as well, like PGP key or signature. Let's take a look at the schema once more, starting from the commit. So we have a commit. The commit refers to exactly one tree. Then the tree must refer to at least one blob and any number of different trees, etc., etc. So the tree can contain tree, that contain tree, and recursively to the infinity, basically, or the capabilities of the file system. And the commits can point to another commit, which their parent or parents. Actually, there can be more than two even. There are some things like an octopus merge that you can, at the moment, merge from multiple branches, not only from the two. And there are also things like, as I said, branches. I didn't mention them before because they are not necessarily Git objects. What branches are is that they are pointers. They are referring a particular commit. There's also one special item in the Git, which is head. And the head refers a particular branch, usually. In some cases, it may happen that the head refers to the commit. This is so-called detached head state that I'll also show in the demo. And while in general you should be worried about detached heads, in Git this is something that's happening day by day and you should not be worried about it at all. I said about snapshots before, and just to clarify, imagine that we have a file and we have then 4 revisions of our repository. And if we hold deltas or diffs and assume that the file changed in the second version, in the, let's say, SVN, we will store the actual delta or diff or what has changed from the original file to the current status. And in Git, we store the whole items, so whole blobs or whole files in like short abbreviation. And the plus is that, imagine that you now need to check out the version 4. If you do it in the SVN, you need to basically get revision 1 and then apply all the diffs. If you have it in Git, you just check out the version 4 and you have the object that is there. During the demo, I will be using mostly Porcelain commands because they are the ones that usually operates. And there are 2 commands from the plumbing one that will be used. One is for hash object, which name is actually quite self-explanatory. So it is used to hash the object and put it in the database. To calculate the hash. It can be used to put it in the database, but I won't use this feature. And there is another magic command, cat file, which I will operate mostly, and it will show you the content of the file and the type of the file. Actually, the content of the blob or another item, content of the object, let's say, and the type of the object. One more thing before we do the demo. You need to know that in the Git, there are 3, let's say, areas. First is a working directory. So this is basically your local file system. Git may know or may not know about the files within the directory. If it does not know, it will be shown as an untracked. If it does know about them, they will be tracked. So they will be either modified or nothing changed with them. Whenever you git add something, it is being moved to the staging area. This means that Git already knows about this file. Git has calculated SHA of the file, and it's about to be committed. What is in the staging area goes into the commit, and then it's saved permanently into the repository. So, let's go. I hope that you can see, this is my terminal, nothing special, empty directory. Let's initialize the Git repo. So we do git init, it's a Porcelain command. It has succeeded, obviously. It's initialized the empty repository, and the .git directory has been created. If we now take a look at it, we will see some things. So we'll see the head, which I said is a pointer to the latest commit on the latest branch. We see some other directories like branches, objects, references, hooks, which we'll not cover into this talk. There's a config file in which you store all the local configuration for your repository. And what is interesting from us is, at the moment, the objects directory. And I will split my screen now. Go here again, and there is a nice watch command that for every second will show us the diff in the execution of the following command. And we want to find items inside Git which are files. And I made a mistake, obviously, because this is live demo. Okay, so we can see we have a following files in our .git directory. As you see, there's nothing in the objects, because there's nothing in our working directory, there's nothing in the staging directory, there's literally nothing in this repo. Let's add it. Let's add a hello text file and put hello git inside. Still, nothing has changed in the Git repository. If we do the git status, we'll see that the Git has found that there is a hello.txt file which is untracked. Let's add it. If we do git add and followed by the name of the file, we have a new object added to the Git database. And it has some SHA. And now I will show you that this SHA is exactly what I presented on the slide. First, let's see how Git calculates this particular SHA. So git hash object, and we passed hello.txt, so we have the SHA. And if you want to calculate it manually, actually for blobs it's easy. For calculating SHA for trees and commits it's way harder, and I won't show it. But for blobs it's easy. So we want to basically print the type of the item, so blob, followed by space, followed by length, including the new line. So we have a hello space, git, and then a new line. So there are 10 characters there. Followed by the null byte, followed by the actual content, hello git, and a new line. And we also need to tell echo to first interpret the /0 character to the null byte, and not to append additional end of the line. And if we pipe it to the SHA soon, we will see exactly the same. So we confirmed that Git calculates the hash exactly as it was described in the documentation. So it's very consistent, you can say. Let's make a commit. Let's see the Git status again. We now have a new file that is in the staging area, and it's about to be committed. So if I now git commit with some commit message, adding hello, you will see that 2 new objects has been created. One for the tree and one for the commit. And Git is nice enough to say that a new commit has been added and it has this particular SHA. Let's see it. We'll use the git cat file, and I will use the -t option to show the type of the object, and I will put the SHA of I believe it's a commit, and it is a commit. If you want to see the commit, we cannot just cut it. If you want to cut it, we will see something that is not very human readable, because we will see that it's actually encoded as a binary file. But the git cat file can encode it for us, and it seems that this particular commit contains, as mentioned, a link to one tree. It has information about who did this commit and the commit message. So let's copy the SHA of the tree and let's examine it. So git cat file, again -t to make sure that it's a tree. It is. And let's see the content. the content, maybe I will try to push it a little bit. Okay. The content is that it contains the information about the permissions of the file, the type of the object, so blob in this case, the SHA of the object of the blob in the Git database, and the name of the file. And finally, if we cut file with this SHA, we'll see the content of our hello.txt. What is nice about Git is that whenever you have more files that has the same content, and you add the file with the same content to the Git, you may notice that nothing has changed in the objects directory because hash is the same. Therefore, the Git does not add another object within the same hash because it's already there. So imagine that you have a repository that has like thousands of files. Let's say it's a Python repository, and you have plenty of underscore or dunder init files, which are mostly empty. These are stored in Git as one file, as one object. Let's see maybe how this Git stores the directories. And let's make the directory. I watched Simpsons a long time ago, so let's use it. Simpsons. And I will simply put the characters there. So echo Bart. What will happen now that we have a new file ahoy, and we also have a new directory to add. So if we add it, some new objects has been created, right? Precisely 2 objects, one for Bart and one for Lisa. If I now commit it, actually I also added ahoy, and you will see that another 2 file has been added, actually 3 in this case, because we added one commit that is pointing to one tree. This tree points to 2 files, and another tree, and this another tree points to 2 files as well. And let's see it. Again, we have a SHA here, and git cut file -p. So this is a commit. This time, this commit has a parent, because it's a second commit in the repository, so only the first commit doesn't have a parent. It points to this tree. So the current tree with the BC1C and following 36 characters points to the 2 blobs, so ahoy and hello, which are pointing to exactly the same content. And it points to another tree, which names Simpsons, and this is a directory. And this tree contains 2 files, Bart and Lisa. Everything is okay here. If I now switch, actually here, I have a GitHub repository, just to show something. I'm adding it, I'm adding a remote here. So git remote add origin and followed by the path. I want to push things there. So git push -u, because I want the local branch to follow the remote one. Origin master. We see that no other object has been created because nothing has changed within the directory. And if we now go here and refresh it, we will have basically what we had on locally. So we have 2 files, and we have directory which also had a file. If I now create a new file here, let's name it March, and this will be March. And adding March. And commit it directly to master in this case. So in our remote directory repository, we currently have 3 files within the Simpsons directory. So we have added a new tree and a new object. And now, if I do git fetch, these all are downloaded. but not applied. We'll see only Bart and Lisa. We need to merge it first, and if we do, it will now be applied in the local repository. Let's now focus a little bit on the branches and the head. So let's create a new branch. So the action of the Simpsons is happening in Springfield, so let's create a branch Springfield. And if we do now the git log, we will see that our head points to the Springfield branch. We are on Springfield. It's OK. If I'm not mistaken, the address of the Simpsons family is like evergreen terrace or something like this. And let's put it into address txt, and let's add it. Okay, some new objects has been added. That's OK. And actually, there's also some place called Moe's. It's a tavern, right? So let's also do it. Moe's into the tavern. Not this one. Git commit. So if you take now a look at the git log, we will see that we here have a commit B29 something something that is basically the master branch, from which we created a new branch, which is the Springfield branch, and we have two commits here. I will stop this watch and I will start another. And what I wanted now to do is to cut the git head, and I will open another terminal session. And here I want to watch for git refs heads for the Springfield. Nope. Of course. Okay. As you can see now, the head pointer points to the Springfield branch, and this branch, in fact, points to a particular commit, and this is the E43 commit, which is here, which is the head of this branch. So everything works, right? Let's now try to switch branch again to master. If we do, the head has changed, and the head now points to the refs heads master. But nothing has changed to the Springfield branch, right? It still points to the same commit. If we now get back, to the Springfield branch, yeah. What? Yes. Oh. Typo? No. I always do the typos. So, sorry for that. So, we're back in this branch, which is incorrectly named, sadly. Let's do the git log again. We see that the head still points to the Springfield branch, or Springfield branch, which then points to the latest commit, which is E4, and this is E4. let's imagine that I want to check out this particular repository. So git check out this particular commit. And if I do, now there is a detached head situation. What happened? It seems that the head index points to a commit, not a branch, and this commit is not in the head of the branch, because the branches also had some heads. And the head on the branch is the latest commit on the branch. And here we see that the head of the Springfield branch points to E43, which is true, but the global head points to a particular commit that is okay from the same branch, but not on the head. Therefore, we have a detached head. There's nothing wrong with it. You can easily use it for checking whether the particular release is working or not working, or things like this. And let's check out the normal branch again, without the G. So now, again, the head points to a proper branch name, and nothing has changed here. I guess that would be it for the demo. And obviously, I did not thought or came onto all of this on myself. I based my talk on the docs and the ProGit book, as well as the wonderful Git internals, how Git works, free not the SHA talk on the YouTube. What I would like you to remember from this talk, besides the fact that I cannot spell Springfield properly, is that the Git is a file-based and content-addressable database, and everything inside of Git is SHA checksummed, and this SHA is the key to the objects. And actually, it's quite easy, as you can see. That's it. Thank you.
Thank you, Dariusz. We have a few questions.
Yep.
What's the dark side and weak points of Git, if there are any?
What's the dark side? So it's hard to answer, actually. Dark side might be if you do not know anything about Git and you actually start from doing these internal things, you may be scared and worried and do not know how to proceed. This can be a dark side. Sometimes you may do some, let's say, bad things, like you are in a rush. Imagine that it's a Friday evening and there is a commit to be pushed, and there is another commit on the remote repository. There's some conflict. You don't know what to do. Then maybe you can be scared a little bit, but then here comes the reflog for the rescue. So I'm not sure that there is a very dark side of it. Nope.
Thank you. Do you believe checkout is the most powerful command nowadays?
From the Git or in general? So from the Git, maybe, because it allows you to get things, although I like commit more because I can add things. In general, probably no. I think there are better commands.
Any Python bindings? Would they make any sense?
No, honestly, I'm not sure, to be honest. I won't guess because I don't know. All I know that some time ago, I came up into a blog post that somebody tries to mimic what is happening inside Git in Python. So there's a Python Git implementation.
Sounds interesting.
And also you can obviously store the source code in Python in the Git, as I did for many, many years. And I will probably continue to do it.
This one I'm very curious about. What are your thoughts about the interactive rebase?
I think this is, in general, I like it a lot. It can be like an, how it's called, ethical question maybe, so the rebase versus merge. I think that this is the point of this question. So honestly, I like rebase more than merging, because the Git history then is cleaner and it allows you to modify things inside of your particular branch, but please don't rebase on the master branch, because this is a hell for the other developers. So within your branch, use interactive rebase as much as you can. If it's already pushed, then don't do it.
Great, thank you. Anybody, any further questions for Dariusz? There is one question, and I'm gonna float over with the mic.
Hey, nice presentation.
Thanks.
What are your thoughts on the SHA-apocalypse? Like, do you think we need to move to
like
a new SHA functions or new hash function?
So I know that there is a plan to introduce SHA to 256 into Git. I think it has been actually added in one of the latest releases. I do not have it yet on my computer, so I didn't use it. Thoughts? I would say that I'm not sure if this is like a real problem, because how many files you can have in a one Git repository? Probably the scope of the single SHA-1 is sufficient. It is not used for hashing passwords, etc. So in this case, obviously, the better hash, the better. The longer hash, the better. But in terms of like having things inside of a one repository, I would say this is not a big problem. Although I know that there are some plans to introduce it.
We have one more.
Yep.
Why is file history lost when you rename the file? Is there no way to show Git that content is the same, or is there a reason for this?
File history lost when you rename the file? I don't get it, sorry. Like, if you rename the file, then it still has the same content. Therefore, it has the same SHA. Therefore, it's the same object within the Git. So I think I'm missing this question, sorry.
I would invite the author to come over after the talk and clarify.
Okay, happy to do it.
And one more, did you had to rescue any commits from the reflogs sometimes?
Yes.
Or what do you think about reflogs at all?
So I think that they are great to know that they exist, and great to know that if something breaks, this is like a first place that you go and check and save yourself.
Thank you.
Thanks.